We're looking at some more optimization notes and examples, and I first wanted to summarize sort of some steps that we tend to use to work these problems. You may have already started to figure these out for yourself yesterday. We talked about them a little bit, but this just formalizes it a little bit more. So when we get to these problems, you want to identify all the given quantities and any quantities that are yet to be determined, and making a sketch is often helpful. We did that a little bit yesterday, especially with the fencing problem. And then we want to determine the primary equation. Remember that this is the one that's going to be maximized or minimized. And then we'll reduce the primary equation to having only one independent variable. We do this usually using a secondary equation if needed. And step 4 is to determine the domain of the primary equation. So what values of the variable make sense? Positives, negatives, does 0 make sense? So you're just determining what that domain is. And then you find the maximum or the minimum using the different techniques we've learned, like the first or second derivative test, sign charts, comparing y values, that sort of thing. So let's do some problems. Example 3. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? This is a problem where it may be helpful for you to draw a picture just to get an idea of what is going on here. So here we have a cube. Now our cube is going to not have a top to it. So it's a box that has a square base. So we have our sides are going to be represented, and I'm using x's. And our height then will be a different variable. It will be h. And we are going to have a surface area of 108 square inches. So we'll go ahead and start writing that out, 108. And remember that the surface area of this box is going to be the area of the base plus the area of the 4 sides. So that's the one closest to us and then the other 3. So that area, the area of the base, is going to be x squared, because that's length times width, and they're the same size. And then the 4 areas of the sides, and each one of those is going to be x times h. So this is our surface area. This is not what we're trying to maximize or minimize. We're trying to maximize our volume. So this is our secondary equation, and we need to write our primary equation. So our primary equation will be volume, and the volume of a cube is simply base times width times height. So that would be x squared times h. All right, we've got 2 variables. We definitely want to get rid of one of them. We'll use our secondary equation to do that. Now, this is a little different from the one we did yesterday. Yesterday, when we were doing just areas and perimeters, it didn't matter which one we solved for. This problem, it's a little bit harder because our x's, we have x squared and then another term with an x in it. And so even if I factor out an x, I'm left with an x in the resulting term. We're really not going to be able to separate x out to solve for x. So the best thing for us to do here is to solve this equation, or secondary equation, for h. So we'd have 108 minus x squared is going to equal 4xh, and then we will divide by the 4x, so we'd end up with 108 minus x squared over 4x. And we're going to plug that into our volume. So volume equals x squared times 108 minus x squared over 4x. And that will simplify. We have x's that will cancel. The x squared here in the front will cancel with the x on the bottom. And so we'd end up with 108x. I'm distributing this leftover x minus x cubed over 4. And just for simplicity's sake, to make that not be a fraction, I'm going to go ahead and do the division here, and we'll end up with 27x minus 1/4 x cubed. And that's a little bit easier derivative to take than when it's a fraction. So let's go ahead and take that derivative because we want to maximize our volume. So v prime is going to be 27 minus 3/4 x squared. We want to find the critical numbers, so we're going to set this equal to 0. It won't be undefined anywhere, so we can just set this equal to 0. I'm going to bring it up here. So 0 equals 27 minus 3/4 x squared. So then x squared will equal 27 divided by 3/4, and so x squared equals 36 when you work that out, and x is plus or minus 6. Okay, we need to check our domain to see if plus or minus 6 is reasonable. And since we are dealing with lengths, heights, volumes, these types of measurements, we know that a negative number doesn't make sense. So in reality, x is going to just equal 6 in this case, and that's our critical number. So we want to check and make sure that this would be a maximum, and so we could do our sign chart to check. Okay, and so plugging the x's back into our derivative right here, when x, the smallest it could be would be 0. So when x is between 0 and 6, then we would end up with a positive number. It would be 27 minus 3/4 times a number less than 36. And so this would be positive, and that would mean that the volume was increasing. And when we plug in a number bigger than 6, then we would end up with a negative in the derivative, which means it's decreasing. And so by the first derivative test, we would see that this is in fact a maximum. So now we just need to find the value of h, because the question is asking what dimensions. Okay, you need to always go back and double check and make sure you're answering the right question. It could have been asking what is the actual maximum volume, and so then you would find the dimensions and find the volume. But here we just have to find the dimensions. So we only need to find h. It doesn't matter whether we plug plug the x in to our original, or we can plug it into our simplified one, either one. And I'm going to plug it into that second one. So h equals 108 minus x squared. X is 6 over 4 times 6. So that's 108 minus 36 over 24. And that's going to equal 3. So we can't just leave it at that. We need to actually go ahead and write out a sentence. And again, I'm sorry I have such a small screen that I'm out of room, but you would say the dimensions that would produce a box with maximum volume would be 6 by 6 by 3. And that's your solution. Okay, next problem. Example 4. An open-top box is to be made by cutting congruent squares of side length x from the corners of a 20 by 25 inch sheet of tin and bending up the sides. How large should the squares be to make the box hold as much as possible? What is the resulting maximum volume? We want to draw a picture, see what's happening. So here we have a sheet of tin, and the dimensions of this sheet of tin will be 20 inches by 25 inches. And we'll end up cutting out squares in all the corners, and the squares will have side lengths of x. And then we'll end up folding up the remainder on each side to make the height of the box. The question says, how large should the squares be to make the box hold as much as possible? So we want to know the size of the squares that will then maximize the volume. And so we need to come up with the volume formula. And volume, when we have a box like this, is length times width times height. And so we need to determine what the length, the width, and the height will be. Since we are going to cut out squares on each side of this sheet of tin, then the actual size of the box here will be 20 minus 2x, because it was 20 from corner to corner, and we cut out 2 squares with a length of x. So the box itself will only have a length of 20 minus 2x. Likewise, the height will end up I'm sorry, not the height, but the width of the box will end up being 25 minus 2x, because we've got this, that leftover piece is what's going to actually be the side, that's the width of the box. And the height of the box is just the actual side of each of the little squares, so it's going to be x. So our volume is 20 minus 2x times 25 minus 2x times x. And when you multiply all of that out, you get 4x cubed minus 90x squared plus 500x. And you really need to go ahead and work that out and just make sure that you've got your algebra straight. In order to maximize this, we take the derivative. So v prime is going to be 12x squared minus 180x plus 500. This does not factor, so we use our wonderful quadratic formula that we love so much. So it's going to be 180 plus or minus the square root of negative 180 squared minus 4 times 12 times 500. All of that over 2 times 12. When you work that out, and this is the type of problem that you would end up using a calculator on, and make sure you go, we're truncating to 4 decimal places, so when you work all of that out, you're going to get x is equal to 3.6812 inches and 11.3188 inches. So remember, we need to always check our domain. We have a 20 by 25 inch sheet of tin. If our x value is 3.6812 inches, that means that we have a length of 20, and we're going to subtract about 7 inches, 7.2 something inches, and that's fine. There's not a problem with that. However, if my x value that I'm cutting out is 11.3188, then I would have a side length of 20, and I would be subtracting twice the x value, and so I would be subtracting 22 inches, and that doesn't work. That's a negative value as a side length, and we can't have that. So 11.3188 is not in our domain. In fact, the largest that x could be would be 10, and the smallest it could be would be 0. So 3 is the only value, the only critical number that works in our context. So we want to do our little sign chart real quick and make sure that this would be a maximum. Remember that we're going to plug this back in to the derivative, and you're going to have to use your calculator for this, and you're going to find that it does, in fact, between 0 and 3.68 will have a positive number, and greater than 3.6812, then we'll have a negative number, and the value x equals 3.6812 is going to result in a maximum volume. So we need to know how large the squares should be, so the squares would be 3.6812 inches by 3.6812 inches. But we also need to find the resulting maximum volume. So you just plug that in to the volume. We're going to plug in the value of x into either one of these. It's probably easier to plug it into the one where we've already multiplied it out. It doesn't matter either way. When you do that, you're going to end up having a volume of 820.5282 inches cubed. Don't forget your units. I think on a previous example from yesterday, I left units off. Just make sure that you always include your units in these problems. On to example number 5. Example 5, a rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page are to be 1.5 inches, and the margins on the left and right are to be 2 inches. What should the dimensions of the page be so that the least amount of paper is used? And so I have a picture that represents the situation, and what we have is the middle inside, that area is 24 inches, square inches, and the margins at the top and bottom are 1.5 inches, and that's from here to here, and then from here to here also, are 1.5. And then the margins left and right are 2 inches each. What should the dimensions of the page be so that the least amount of paper is used? This one is a minimum. We are wanting to minimize the amount of paper used. That's area. This is a rectangle, so area equals length times width. Let's assign some letters, and I would say that this is our length. What I know is that I've got, excuse me, margin here and margin here of 2, and then I have this distance, which is actually the area of going to help calculate that area of the inside, which we said was 24. So I'm going to let the inside part be x, and then this outside area would be x plus 4 for the 2 margins. You could do it the other way. We could set it up like we did the previous problem and have this whole distance be x, and then the inside distance would be x minus 4. Either way, I'm just choosing to put the x on the inside for this particular problem. Likewise, on the outside, this is going to be, I'm going to call this vertical piece here y, and so this would be y plus 3, since we have a margin top and bottom 1.5 each. So the area of this entire rectangle is x plus 4 times y plus 3. I want to replace one of these particular variables so that we only have one variable that we're working with. Doesn't matter which one in this particular case, since we're just dealing with areas here. This goes back to ones like we did last time, yesterday. So we're going to use a secondary equation that's relating the area of the inside rectangle, and that was an area of 24 square inches, and that's just x times y. So this makes it easier for us to use this information. It's a lot neater of an equation, less messy to do it this way than if we had reversed it and had x be the whole outside, so that we would have x minus 4 and x and y minus 3 in this equation. It's just a little bit easier. All right, let's solve. I don't care. We'll solve for x. So x is going to equal 24 divided by y. You could do it the other way, and that would be fine, whatever you prefer. So now we're going to plug this in to our primary equation. So area is going to equal 24 over y plus 4 times y plus 3. And then I'm going to go ahead and multiply it out just so I don't have to deal with product rule. And when I do that, I'm going to end up with 24 plus 4y plus 72 over y plus 12. I'm showing you the interim steps. and then that equals, when you combine everything, that is going to be 4y plus 72 over y plus 36. Take a minute if you need to work out that algebra, make sure you've got it. It can be a little messy with that fraction. Now we want to take our derivative so that we can minimize this, and so it's going to be 4 minus 72 over y squared. We want to set this equal to 0 and solve. Again, this is a case where I just tend to get a common denominator and deal with the fraction that way. You don't have to do that, but you just want to be careful in solving these. So since for the fraction to be equal to 0, the numerator is 0, so 0 equals 4y squared minus 72. So y squared equals 18, and y will equal plus or minus the square root of 18. Once again, we're dealing with lengths, so it's going to equal just the positive square root of 18. This is the y value of this length of or height of the inside square. So we want to find the x value. We're going to plug our y value in to the original function, and we're going to get x equals, so I'm plugging it in up here, x equals 24 divided by the square root of 18. You can leave it like that. That's a nice exact answer, or you could get the decimal. Now we have to be very careful because the question wasn't, what are the dimensions of the inside square? The questions are, what should the dimensions of the page be? So we've got to go back and add our margins in and get our final answer. So I went back and I went ahead and converted the square root of 18 to the decimal using my calculator. It's approximately 4.2426. I don't think I can get the 6 in there. And 24 divided by the square root of 18 is approximately 5.6569. So then I'm going to have to add 3 to my y value, which is actually this one down here, and I'm going to add 4 to my x value, which was this one up here. I know they're kind of backwards. Okay, so our dimensions then, I'm out of room, so let me erase this one. Our dimensions are going to be 9.6569 inches by 7.2426 inches. Write a nice little sentence, make it a little neater than my scribbles here, and that would be the dimensions of the page to have a minimum amount of paper being used. I know we're running a little bit long, but I have one more example. It will not be as long as these, I promise, but you do want to see it. Example 6. In an autocatalytic chemical reaction, the product formed is a catalyst for the reaction. If Q sub 0 is the amount of the original substance and X is the amount of catalyst formed, the rate of chemical reaction is dQ over dx equals Kx times the quantity Q sub 0 minus X. For what value of X will the rate of chemical reaction be greatest? This is a problem that, first of all, we don't need a picture for. There's not a geometric representation of what's happening here. The other thing is I know that there are a whole lot of letters out there in that equation, but we want to just relax about it because X is our independent variable. That's the one we're concerned with. We want to know what value of X will maximize this. We know it's maximum because it says greatest. That means that we can treat everything else as a constant. So K would be a constant and Q sub 0 would be a constant. And of course dQ dx, you know, here it's just like y or something. It's just telling us sort of the name of the function. The trick, however, to this one that you have to be careful about is that it says for what value will the rate of chemical reaction be greatest? So you need to ask yourself, am I maximizing the equation given, or am I maximizing the derivative of the equation given? Well, this equation that they've given us is already the rate of chemical reaction. So even though it's asking for a maximum rate, we will not actually maximize the derivative because we've already been given the derivative. So be careful, stop and look. You have to ask yourself, what have I been given and what is it asking for and how are those related? So we're just going to go ahead and write out this derivative. dq dx equals kx times q sub 0 minus x. And we want to maximize using the value of x. Because we're treating everything else as constants, then we don't need a secondary equation. We're not going to actually get rid of the k or the q sub 0. We're just going to worry about the x itself. So I'm going to take the derivative of this derivative in order to find the critical numbers of this particular rate. So we'll write that using our second derivative notation. And now you can use the product rule here, but I actually chose to go ahead and distribute just to make life a little easier. And this would be kx squared. And if you want, since we're treating the q sub 0 as a constant, you could even write it in this order just to remind you that that's constants. So then the derivative of this piece, k and q sub 0 is the coefficient, and so that derivative will just be kq sub 0. And then here we have x squared with a coefficient of k, so that's going to be minus 2kx. That's our derivative. We want to set it equal to 0 and solve. So 0 equals k cubed 0 minus 2kx. And so then x will equal q sub 0 over 2 when you work it out. That's telling us that our value for x appears to be whatever the half the value of the initial catalyst, that this might be when we have our maximum. This is our critical number. So this seems a little odder to try to do a sign chart since we don't actually have an explicit value, but we can still work it out because our lowest amount would be 0. So if we have a number between 0 and q sub 0 over 2, if I plug it in to the original, let's actually plug it in up here, to the original, the derivative of the rate of change, then you would end up with k q sub 0 minus 2k q sub 0 over 2. And those go away. So if we have a number that's less than the q sub 0 over 2, then we would end up with a positive number because this difference would be positive because k q sub 0 would be greater than what we were subtracting. And then if we have where x is bigger than q sub 0, then we would end up with a negative number. And so it is, in fact, according to the first derivative test, it is a maximum. You could do this, because this is a little odder to try to do a sign chart, you could do this by taking the next derivative and checking the concavity. If you wanted to, I'll just show you that real quick. So this would be like this, and you would end up with this first term derivative would be 0, and the second term the derivative would be negative 2k, which is a negative value, which would mean that the original function is concave down, and since we had a critical number in a concave down interval, then it would have to be a maximum. So we are in fact maximizing the rate of chemical reaction. So be sure that you write out your sentence saying that the rate of chemical reaction would be maximum whenever X equals Q sub 0 over 2. All right, that's it. We ran a little bit longer than I anticipated. Thanks for hanging in there. Be sure to come to class tomorrow with any questions that you have, and we'll go over them and practice some of these problems tomorrow. Have a good evening.